True to their name, black holes are always dark, strange, and mysteriously scary. Today, black holes are one of the main things humans study beyond our universe. But did you know that it wasn't until 2019 that we actually got the first real picture of a black hole? Before that photo came out, black holes only existed in theories or complex physics equations. But after that historic moment, everything became clear. Black holes really do exist, and everything people said about them before was true. To us, black holes are mysterious and terrifying objects that also hold the key to understanding the universe. So, what do we actually know about them? How scary are they really? Could anyone survive if they faced a black hole? Today, Discovery MST will dive into the story of one of the most powerful monsters in the cosmos and how we might survive if we ever encounter one. As usual, don't forget to leave a like and subscribe to support the creators of this video. Hope you enjoyed today's content. A black hole is a region in space-time where gravity is so strong that nothing, not even particles or electromagnetic radiation like light, can escape. According to General Relativity, if enough mass is packed into a small enough space, it warps space and turns that area into a black hole. Surrounding a black hole is a surface called the event horizon. Once something crosses this boundary, it can never get out again. Black holes are called black because they absorb all radiation and matter that pass through the event horizon, just like a perfect black object in thermodynamics. Based on how they form and their properties, black holes can be divided into three types: stellar mass black holes, intermediate mass black holes, and supermassive black holes. Stellar mass black holes are about 10 times the mass of our Sun and form when massive stars collapse. These are the most common black holes, and many have been discovered so far. Intermediate mass black holes fall between stellar mass and supermassive black holes, with masses ranging from a few thousand to a million times the mass of the Sun. However, scientists still debate how these black holes form. Supermassive black holes are the heaviest in the universe, weighing millions to billions of times the mass of the Sun. Scientists believe they form through special processes, like the merging of many smaller black holes or dense star clusters. That means a black hole can also form when two or more black holes merge. Even though a black hole is defined as a completely dark or invisible region, we can infer its existence by how it interacts with the surrounding matter and light radiation. Matter falling into a black hole forms an accretion disk. Here, the matter collides and rubs against each other, turning into plasma that emits strong high-energy radiation, making the area around the black hole one of the brightest objects in the universe. If a star orbits a black hole, the shape and timing of its orbit lets astronomers calculate the black hole's mass and distance from us. This info helps them distinguish whether a super-dense object is a black hole or a neutron star. Using this method, many black holes have been found in binary star systems, and at the center of the Milky Way, there's a giant black hole about 4.3 million times the mass of our Sun. One common misconception about black holes is that they're just extremely dense objects. As mentioned earlier, black holes form from very dense matter, but the black holes themselves aren't really things in the usual sense. Our Sun is about 1.5 million kilometers in diameter. But if you compress the Sun down smaller and smaller until it became a sphere only about 6 kilometers across, its huge mass would force it to keep shrinking and eventually disappear. There'd be no surface, no matter making it up, just an empty region of space. If you got close to a black hole, you might not even realize something terrible was approaching. Imagine you're on a space journey to enter and explore a black hole. How do you think that trip would go? Would you survive and escape? To understand this, we need to take a moment to grasp what curved space and time inside a black hole mean. Since the 20th century, Einstein's equations have described how space and time react to matter and energy. You can look up Einstein field equations if you want to dive deeper into this. If you throw something around Earth, you see it moves in an arc. If you throw it fast enough, you can put it into orbit, and it will follow a perfect circular path. Examples include the International Space Station, ISS, which moves at over 28,000 kilometers per hour in a circular orbit while actually falling around the planet. The orbits of satellites in the ISS show what circular paths in space look like. So, if you're exploring space and don't realize you're near a black hole, you could suddenly be right next to it because no light escapes from around it. A black hole acts like a lens. The light around it bends due to the curvature of space. But instead of focusing or reflecting light, it bends light infinitely. We'll explain this more clearly when we talk about the photo of a black hole later. Back to the journey. If you realize you're close to a black hole, it's already too late. You're basically trapped, and no amount of struggling will help you break free. Even if, somehow, you manage to pilot your ship out, the first big problem you'll face is the fuel you're carrying. Let me help you understand why by describing the difficulty of escaping Earth's gravity. Do you know how fast a spaceship needs to go to escape Earth's pull? It has to reach a speed of 7.9 kilometers per second just to avoid falling back. On the Moon, that speed jumps to 11.2 kilometers per second. And to travel further, you need even more speed. How do you reach that speed? Only rockets can do it. To get an object moving at 7.9 kilometers per second and escape Earth's gravity, you need a massive amount of energy. For example, a 1-gram object escaping Earth would require as much energy as powering 1,540-watt light bulbs for an hour. Rockets work by shooting gas out the back to create thrust. The faster the gas shoots out, the faster the rocket goes. To hit those crazy speeds, you need super fast exhaust and tons of fuel. Say your rocket's exhaust speed is 4,000 meters per second. To reach escape velocity at 11.2 kilometers per second, your rocket would need fuel weighing several times more than the rocket itself. Now imagine a black hole's gravity, millions of times stronger than the sun's. Even if your ship could handle that gravity, where on Earth would you get the insane amount of fuel needed to reach escape velocity? Once you're caught in a black hole's gravitational pull, you can't get out. At this point, the question of whether you can survive and escape is clear. There's no way at all. As you get closer, not only is space bent, but time is too. The moments on your watch, your breaths, your thoughts, all seem to slow down compared to someone far away. To you, time feels normal because you're synced with the black hole's warped frame of reference. But from an outsider's perspective, your watch would appear frozen completely as you near the black hole's infinitely warped center. But that's not all. If you somehow survive long enough, you'll cross the event horizon, the point of no return where nothing, not even light, can escape. As you get pulled toward the event horizon, you'd experience a weird effect called spaghettification. It's one of the most famous effects caused by black holes. And honestly, it's easy to picture. Anything that gets too close to a black hole gets stretched out like spaghetti noodles. This happens because the gravitational pull isn't the same all over the object. Imagine you're being pulled toward a black hole feet first. The gravity tugs much harder on your feet than your head. It doesn't just squash you flat, it stretches you out long. Even worse, your limbs won't stay connected to your body's center but will get pulled in different directions. The result? Your body stretches out like it's made of plastic. Think of it like Mr. Fantastic from the superhero comics, but way, way worse. It stretches and tears apart you and your spaceship down to the molecular level, until you just vanish into nothingness, no longer any kind of normal matter. At this point, you basically don't exist anymore. But let's keep going with the theory. If, somehow, you and your ship manage to get past this zone, what awaits deeper inside the black hole? Things get even more extreme the further in you go. The center of a black hole, called the singularity, is a place our current physics just can't explain. It's got infinite density and gravity, but it's incredibly tiny. Here, classical physics breaks down, and only a mix of quantum mechanics and general relativity can even try to describe what's going on. In this harsh, mind-boggling environment, any matter that falls into the black hole doesn't exist in our familiar universe anymore. It might completely disappear or become part of the black hole itself. We don't know exactly what happens to that matter, which just adds to the mystery of black holes. That's why there are all kinds of fascinating theories if you ever make it to the singularity. You've probably seen the 2014 movie Interstellar. In it, after being pulled inside the black hole, the main character crosses the event horizon and drifts into a 5-dimensional space inside. This 5-dimensional space is shaped by gravity, so no signals, light, or sound can escape from it. The idea of a fifth dimension in the movie was inspired by Kip Thorne, a famous theoretical physicist from Caltech. This theory is cool because it describes the black hole like a cosmic photocopier. People think black holes have another kind of surface. Stuff doesn't just get sucked all the way in, instead, it falls onto some kind of surface. Think about anti-counterfeit stamps that have a holographic surface. Black holes might have a similar kind of surface. If that's true, you might actually be okay on a surface inside a different dimension. But this surface has everything needed to look like a regular 3D object. So you'd be fooled into thinking it's real, even though it's just a holographic projection. This means that maybe, right now, we're actually living inside a black hole. But things could be way crazier than you imagine. Not just a patch of space, the entire universe might be inside a black hole. That could mean black holes might hold the key to understanding where the universe came from. A lot of people have wondered, if the Big Bang started everything, what was there before the Big Bang? We know the Big Bang happened about 13.7 billion years ago. Just 10 to the minus 36 seconds after it, space expanded like a balloon. Before the Big Bang, some researchers think the universe existed as a single, infinitely dense point called a singularity. That singularity burst and has been expanding ever since. This idea is basically the opposite of how black holes work. Black holes are also infinitely dense points in spacetime, but instead of expanding and pushing things out, they pull everything in. Still, if our universe is inside a black hole, and it's constantly pulling in matter from outside, then the inside would be expanding more and more. Could forming a black hole actually mean creating a new universe inside it? Right now, some say black holes can't get big enough to hold an entire universe. But the biggest black hole we've found, Ton 618, is unbelievably huge. Its event horizon is over 390 billion kilometers wide, 43 times the diameter of our solar system. That's still way too small to fit a universe, let alone everything else. So how could the entire universe fit inside a black hole? Our universe is expanding so fast that we'll never reach its edge. Because of the way space-time curves, our universe might be shaped like a donut. If you try to go beyond the edge, you just end up circling back to where you started. Just like you can't reach the edge of the universe, you can't get to the center of a black hole either. So if our universe is inside a black hole, inside another universe, it means reality is made up of a bunch of overlapping universes, each with black holes containing their own universes. If every black hole holds its own universe, then the true shape of reality might be like a tree branching out over and over. The black hole universe theory could also help solve some other physics mysteries. For example, it might explain dark energy, the mysterious force driving the universe's expansion. Nobody knows what dark energy really is, or why the universe doesn't just keep expanding but does so faster and faster. What if that dark energy comes from matter outside our black hole universe being sucked in? Matter from outside turns into energy inside and pushes our universe to expand faster? This could also explain the early, rapid expansion of the universe right after the Big Bang. Even though black hole theory can answer some questions, it also raises new ones. We don't really know how stuff from outside turns into energy inside. But let's say we could figure all that out. How would we even check if we're inside a black hole? That'll probably have to wait for bigger scientific breakthroughs. Here's another cool idea about black holes. We might be able to use them to time travel. Like mentioned earlier, when space stretches, time does too. A clock near something heavy runs slower than one near something lighter. So, a clock near a black hole would tick slower than one on Earth. 1 year near a black hole could equal 80 years on Earth. You might have seen this in the movie Interstellar. This means black holes could be used to travel to the future. If you want to visit Earth's future, just fly close to a black hole and then come back. If you get close enough, your clock slows down, but you can still escape, as long as you don't cross the event horizon. Of course, this is all theoretical, because right now, no spaceship has the power or fuel to break free from a black hole's pull. What about the past? That's where things get really interesting. A black hole bends time infinitely. Imagine taking a piece of paper and taping its ends together to make a loop. That's what a black hole can do to time. It creates a natural time machine. If somehow you could jump into that loop, you'd be traveling along a path through space and time, starting in the future and ending in the past. Inside this loop, cause and effect get really confusing. Things that happen in the past create the future, which then causes things to happen in the past again. Suppose you find a black hole and want to use a reliable spaceship to visit the dinosaurs. First, you can only travel into the black hole's own past. If the black hole formed after the dinosaurs went extinct, you can't go back that far. Second, you might have to cross the event horizon to get into the loop. That means, to escape the loop at a specific time in the past, you'd have to get back out of the event horizon. You'd have to move faster than light, which is impossible, as we've mentioned many times. So, although it's fun to think about black holes bending time, visiting dinosaurs or jumping to the future isn't going to happen anytime soon. Black holes are some of the most mysterious places in the universe, but our understanding is still limited. Scientists are working hard to study their nature and behavior, hoping to uncover the secrets they hide. By observing the radiation around black holes and using advanced simulations, we can learn more about the harsh environments and incredible sights matter experiences when falling into one. Still, the day we truly explore a black hole firsthand isn't coming soon. You might not believe it, but even after hundreds of years of study, we only got the first actual image of a black hole a few years ago. Our history of black hole research is like a centuries-long TV series. That first image was the result of countless brilliant minds working over hundreds of years. The idea of a massive object so dense that light can't escape it was first proposed by a man in a letter to Henry Cavendish, the famous British physicist, back in 1783. Then, Michel pointed out that if a sphere with the sun's mass had a radius about 500 times smaller than the sun's, a falling object would hit the surface faster than light speed. Assuming light is pulled by gravity just like any other object, all light from the sphere's surface would be pulled back by its gravity. In 1796, Pierre-Simon Laplace, a French mathematician and astronomer, also mentioned this idea in the first 2 editions of his book about the solar system. These hypothetical, dark spheres, were forgotten in the 19th century because most physicists thought light had no mass and couldn't be affected by gravity, so it couldn't be pulled back. It seemed like this idea would stay buried in science forever, until one guy came along and changed everything: Albert Einstein. In 1915, Einstein completed his general theory of relativity, which had predicted that gravity bends the path of light. Just 2 months later, Astronomer Karl Schwarzschild found the first exact solution in Einstein's equations that describe the gravitational field of a point mass or a uniformly distributed sphere in a 4D spherical coordinate system. This math is pretty complex, but it introduced something now called the Schwarzschild radius, a weird property where spacetime described by Schwarzschild coordinates becomes discontinuous. Simply put, the Schwarzschild radius, or gravitational radius, of an object is the critical size where, if the object's radius is equal to this value, it becomes a black hole. Many scientists have since studied this and made great progress. This discovery kicked off the golden age of general relativity and made black hole physics one of the main fields in modern physics. During this time, we made a new discovery about Japunsa V, stars that spin really fast around their axis back in 1967. But even then, physicists still thought pulsars were like black holes. Then, in the early 1970s, Hawking and other scientists kickstarted the field of black hole thermodynamics. These laws describe black holes' properties in ways similar to the laws of thermodynamics, linking mass and energy, the event horizon's area to entropy, and surface gravity to temperature. In 1974, Hawking nailed these connections by proving that quantum field theory predicts black holes emit radiation proportional to their surface gravity. The term, black hole, was first used by physicist John Wheeler in a 1967 lecture. Once Wheeler popularized it, the term quickly caught on among scientists and the public. The journey from black holes' discovery to their name was long and full of twists. But getting the first real image of a black hole was even tougher. Take a look here. The photo we're seeing is the result of a collaboration between 8 observatories worldwide and more than 200 top astronomers. Scientists from the EHT project, the Event Horizon Telescope, used 8 telescopes spread across the globe to create a virtual telescope the size of Earth to capture images of a black hole. The image they revealed is of the black hole at the heart of galaxy Messier 87, about 55 million light-years from Earth. This is the first ever real photo of a cosmic black hole. All previous pictures were just imaginative renderings or computer simulations based on data and scientists' analyses. But unlike those simulations, this photo isn't a black sphere with gigantic swirling cosmic matter around it. The first image of Messier 87's black hole is just a strange ring of yellow and orange. Why is it like that? Have we been imagining black holes wrong all along? Why isn't it as dramatic or beautiful as we thought? The simple answer is that movies rarely get it right. Even this photo isn't a direct picture of the black hole itself. What we're actually seeing is the shadow of the Messier 87 black hole. Theoretically, black holes are invisible objects, but we can see their edges in the event horizon under certain conditions. For example, if a black hole sits inside a bright area, like a glowing gas disk, it creates a dark spot, essentially a shadow, against that light. The black hole in M87 isn't the closest to Earth, but it's the biggest, making it the best target for this kind of observation. In the image released by scientists, the black circle in the middle is actually just the shadow of the cosmic black hole. Its boundary is made up of glowing matter surrounding it, but the color of the circle isn't the true color of the gas and dust around the black hole. The orange-yellow you see is a color chosen by EST scientists to show how bright the surrounding matter is. Yellow means the brightest, red is less bright, and black means little or no brightness at all. If we look at the spectrum, the light from the ring around the M87 black hole would probably appear white with a hint of blue or red. Over time, our understanding of black holes has gotten better and better. We can dream about a future where this cosmic monster is tamed. At that point, all the mysteries about time, matter, event horizons, or even the fifth dimension will finally be clear. What do you think about studying black holes? Are they worth our effort? And if we crack their secrets, could it open a whole new chapter in the history of science? Thanks so much for listening and supporting Discovery M Street. That's it for today's video. Looking forward to seeing you in the next ones. Wishing you a great day with your family.